Alright, so we'll start a new lesson today, and remember you guys are having a short quiz tomorrow, just like we will up until the end of the year. So today is the 30th, and today we're going to be doing section 10.1, and it's called Real Exponents and Exponential Functions. Alright, now what an exponential function is, when you have like x to the second, this is called the exponent. But an exponential function has the variable as the exponent. So that would be like y is equal to like 2 to the x. That would be an example of an exponential function. So let's just do a little comparison, and we'll look to see what the difference is between, say, like y equals x squared and y is equal to 2 to the x. I'll pick different values of x. We'll make a little table. And let's see what we get. So I'll go by 1s on the x-axis, and I'm going to go up by 5s on the y-axis. You'll see why in a minute. Alright, so I'll do x squared in via red. So if you put -2 and -2 to the second is 4. -1 to the second is 1. 0, 1, 2 squared is 4, 9, 16, and 25. So -2 would be 4, 1, 0, 1, 4, and 3 is 9, 4 is 16, and 5 is 25. So you get this shape, like a parabola. And that's nothing new, but we haven't seen 2 to the x before. So 2 to the -2nd, remember, is 1 over 2 squared, which is 1/4. 2 to the -1st is 1 over 2. 2 to the 0, anything to the 0 is 1. 2 to the 1st is 2. 2 to the 2nd is 4. 2 to the 3rd is 8. 2 to the 4th is 16. And 2 to the 5th is 32. So let's graph this. 1/4, 1/2, 1, 2, 4, 8. 2 to the 4th is 16. 2 to the 5th is 32. So we have this kind of shape. That's an exponential graph. We're going to be talking more about the graphs in later sections, but you could see that this graph grows the fastest. Right? When you look at the two graphs, the exponential growth is the fastest, which is why a lot of people are concerned about this virus and why I'm teaching you from the computer like this. It's because the virus growth grew exponentially and a lot of people are infected. So before we get started, I just want to go over some rules with exponents. We all know these already. First rule is the zero power property. The zero power property says anything to the zero power is 1. We know that the product property says that x to the second times x to the third, as long as the bases are the same, we could add the exponents. Quotient property says if we're dividing the same bases, we could subtract the exponents. Power property says that whenever you have a power to a power, you multiply. And the last one is the property of equality. This might be new for us. Property of equality says if you have like x to the third is equal to x to the n, then 3 would equal n. As long as the bases are the same and they're equal, that means the powers are the same. It's pretty easy. So I have a few examples to go over today, not a big deal. Let's take a look at some examples. So I'm just going to be asking you to simplify. Let's say 7 root 2 times 7 root 3. Using the properties, they do have the same base, so we could add the exponents. But remember, with radicals, if they don't have the same radicands, you can't combine them. You can't say that's 7 to the root 6 power or root 5. It doesn't work like that. You can only combine radicals if they have the same radicands, which are the inside numbers. So this would be 2 root 3. But because these are different, you have to keep them separate. This would be the answer. What about if I gave you 8 to the root 3rd power to the root 5 power? Power to a power you multiply. When you multiply radicals, you multiply the inside numbers, you multiply the outside numbers. So 8 root 15 would be the answer. All right, so now let's solve some equations. What if I asked you to solve, let's see here, 3 to the 4th is equal to 27 to the m minus 1. Now the whole idea is we want to get the bases the same. So I could write 27 as 3 to the 3rd. And the reason why we want to do that is because we could use a power property. Power to a power, remember, you multiply. And if the bases are the same, that means that the powers are the same. And this is how you do these kind of problems. So you look to see how could you get the same base, and it's usually a power of a prime number. Let's try another one. How about 1 over 25 to the 2n power is equal to 5 to the n minus 5. Now 25 we know is 5 squared, but because it's as a fraction, let's write it like this. Let's write 1 over 5 to the second to the 2n power equals 5 to the n minus 5. We could switch the position using the reciprocal property. This is really 5 to the negative second. So 2n is equal to 5n minus 5. Power to a power, we multiply. And because the bases are the same, the powers have to be the same. So n would be 1, not a big deal. All right, maybe a few more here. How about this? How about 2 to the 3m plus 1 is equal to 64? Well, 64 is a power of 2. It's actually 2 to the 6th. So this one's kind of easy. The bases are the same. So 3m plus 1 would be 6. So 3m would be 5, m would be 5/3. How about 16 to the 2m plus 1 is less than or equal to 1 over 32. So the inequality is not going to make a huge deal here. Let's try to solve this like an equation first. So 16 is really 4 squared, but I can't write 32 as a power of 4. So think about your prime numbers. 2, 3, 5, 7, 11. You want to try to write the base as one of those to a power. 16 is really 2 to the 4th, and 32 is really 2 to the 5th. So now let's power to a power, we multiply. And then we could use the reciprocal property. And we do get the same base, so we could just cancel out the bases. The inequality is not going to make any difference because we're not dividing by a negative. And here's our answer. Okay, how about this one? 6 to the 2n minus 1 is greater than 1 over 216. Now it's tricky, right? Because 6 isn't 2 to a power, it's not 3 to a power, it's not 5 to a power, so 6 is going to be our base there. But 216, you might have seen that before. That's actually 6 to the 3rd. So the hardest part is just recognizing that. Then you could set the bases the same. And you get n is -1. This was an inequality. We didn't divide by any negatives, so we should just keep the inequality then. We don't have to worry about extraneous solutions here. A couple more examples. I'm going to ask you to simplify these. Just 2 more here. The first one looks like this. X to the root 2 power plus y to the root 3 times x root 2 minus y root 3. Now, the reason this looks a little bit different is because you do have an irrational exponent, but we're just going to do it like we usually do. First terms, outer, inner, and last. Okay, power to a power, same base, we add. Root 2 plus root 2 is 2 root 2. These are not the same base, so we have to keep them separate. And then these are the same base, we could add root 3, and root 3 is 2 root 3. These middle terms actually cancel each other out, and your final answer for this would be x to the 2 root 2 minus y to the 2 root 3. All right, there's one more example today. And that's y root 2 plus x root 5 all to the second power. Now we know we're not going to do this because then I'm going to disown you. So the way we have to do a problem like this is we would write it twice. And it's the same kind of problem that we just did. Multiply the first terms. Outer terms. And then the last terms. Same base we had. Now, these are actually the same terms. I mean, they have the same variables to the same power. So we have 1 x root 5 y root 2 plus another x root 5 y root 2. That's going to be 2 x root 5 y root 2. And then, of course, our last term, same base, so we add the exponents. And that's the lesson today. For homework, I would like you to please do is practice 10-1. I would like you to please do the evens. All right, thank you so much. Have a nice day.